Hello everyone, welcome to Basic Electronics Tutorials. In this video, I'm going to take up the first numerical on half-wave rectifier. Let me read out the question first. A half-wave rectifier circuit is supplied from a 230 volt 50 Hz supply with a step-down ratio of 3:1 to a resistive load of 20 kilo ohms. The diode forward resistance is 85 ohms, while the transformer secondary resistance is 10 ohms. Calculate part 1 of the question, maximum, average and RMS values of the current. Part 2, DC output voltage. Part 3, efficiency of rectification. And part 4, ripple factor. Right, let us now understand the question. We are told there is a half-wave rectifier that is supplied from a 230 volt 50 Hz supply and the transformer turns ratio is 3:1. In the diagram shown here, I have drawn the half-wave rectifier circuit for the specification given in the numerical. As you can see, the input of the transformer is supplied with a 230 volt 50 Hz supply. The transformer turns ratio is 3:1. The diode has a forward resistance of Rf equal to 85 ohms. Load resistance is 20 kilo ohms. Let us now quickly write down these given parameters. The input supply voltage is 230 volt. Please note this is at the primary. You should also note that this is the RMS value of the voltage. The diode forward resistance is 85 ohms. Load resistance is 20 kilo ohms. And the transformer secondary resistance is 10 ohms. Let me denote this as RS. Right. Now we are supposed to find the secondary transformer voltage, and for finding that I'll be using the relation between the turns ratio and the voltages across the primary and secondary of the transformer. They are related by the equation N1 divided by N2 equal to Vp, which is the voltage across the primary, divided by Vs, which is the voltage across the secondary. It is given that the value of N1 divided by N2 is equal to 3:1, which is 3 by 1. So now I will substitute this into the equation 1, which is the relation between the turns ratio and the voltages across the primary and secondary. So it would be 3 divided by 1 equal to Vp divided by Vs. Therefore, Vs is equal to Vp divided by 3, and since Vp is equal to 230 volt, the value of Vs is equal to 76.667 volts. Please note this is the RMS voltage across the secondary. Let us now start with the part A of the numerical, which are to find the maximum, average and RMS values of the current. Please note this is a very simple series circuit at the secondary. So the current across the diode when it is conducting is the same current that flows across the load resistance as well. That is why the current in the circuit is shown as IL. Since we just found the RMS value of the transformer secondary voltage, let us find the maximum value of the transformer secondary voltage and use that to find the maximum value of the transformer secondary current. So I'll start part A of the question by first finding the maximum value of the transformer secondary voltage. Let me denote it as V secondary maximum, that is Vs max, and this is equal to root 2 multiplied by the RMS transformer secondary voltage, which is Vs. Please note we just calculated Vs above. So this is equal to root 2 multiplied by 76.667, and this will be 108.423 volts. This is the maximum value of the transformer secondary voltage. Once we have found the maximum value of the transformer secondary voltage, let us now move on to find the maximum value of the transformer secondary current. Let me denote it by I max, and this is given by V secondary max, what we computed just above, divided by all the resistances in the circuit. First of all, let us write the secondary transformer resistance, that is Rs, plus the diode forward resistance, that is Rf, plus the load resistance RL. Let us now substitute values into this equation. Vs max is 108.423, Rs is 10 ohms, Rf is 85 ohms, and the load resistance is 20 kilo ohms. Simplifying this, you will obtain the maximum value of the transformer secondary current as 5.39 milliamperes. If you come back to the numerical, you see that the part A also asks us to find the average as well as the RMS values of the current. For that, you have to note that we are dealing with a half wave rectifier. So, I will be using the standard formulas for average and RMS values of the current. Let me find the average value of the transformer current first. I'll denote it as IAV, stands for I average. I can also call it as IDC because it is one of the most common notations for average value of the transformer secondary current. And this is equal to I maximum divided by pi. This is the standard formula for half wave rectifier. So this is equal to I max, which is 5.39 milliamperes divided by pi, and this will result in 1.71 into 10 to the power of minus 3 amps, that is 1.71 milliamperes. Lastly, I'll move on to find the RMS value of the transformer secondary current. I'll denote it as I RMS, and this is equal to I maximum divided by 2. I maximum is 5.39 milliamperes divided by 2. Therefore, the RMS value of the transformer secondary current is 2.695 milliamperes. Right, that is the solution for part A of the question. Let us now move on to part B, which is to find the DC output voltage. This one is pretty simple because the equation for DC output voltage is simply the DC output current multiplied by the load resistance. Let me denote the DC output voltage as VDC, and as I said, this is equal to IDC or I average multiplied by load resistance RL. IDC is 1.71 milliamperes, RL is 20 kilo ohms. Therefore, the value of DC output voltage is 34.2 volts. That is a solution for part 2 of the question. Coming back to the question, the part 3 of the question is to find efficiency of rectification. Let me now write the formula for the rectification efficiency. It is denoted by eta and is given by eta is equal to PDC divided by PAC, where PDC is the DC output power and is given by PDC equal to VDC multiplied by IDC. We have previously computed VDC, which is this, and this is equal to 34.2 volts multiplied by, we have also computed IDC and it is equal to 1.71 milliamperes. So, the value of DC output power is 0.0584 watts. Coming back to the equation for efficiency, which let me call as equation 2, we have to now compute PAC. What is PAC? PAC is the AC input power and is given by PAC equal to Vrms multiplied by Irms. Please note this is across the secondary of the transformer. It should be noted that we have not computed the value for Vrms. However, I can express Vrms in terms of Irms by simply representing it as a product of current and all the resistances. So, Vrms can be written as Irms multiplied by all the resistances in the circuit, starting with the transformer secondary resistance, the diode forward resistance and the load resistance. This is the representation for Vrms. Then we have Irms, which I will write here. Multiplying the terms, I will obtain the final expression as, please note we have already computed Irms and all the values of the resistances are also available. So let us now substitute here. Irms is 2.695 milliamperes, Rs is 10 ohms, Rf is 85 ohms and Rl is 20 kilo ohms. Simplifying this, you will obtain the value of PAC as 0.1459 watts. Now, having computed both PDC and PAC, let us now substitute these values back into equation 2 to find the rectification efficiency. So, rectification efficiency eta equals PDC divided by PAC. PDC value is 0.0584, PAC value is 0.1459 and therefore it is equal to 0.4002. In terms of percentage, it is 40.02%. That is the solution for part 3 of the numerical. Lastly, the part 4 of the numerical is ripple factor. This one is a quite straightforward question because the ripple factor for a half-wave rectifier is a constant and is equal to 1.21. It does not change even if we vary other parameters of the circuit. So we can simply conclude that the ripple factor of a half-wave rectifier is 1.21. We generally denote ripple factor by gamma, and as I said, this is equal to 1.21. That is the answer for part 4 of the question. Well, with that we have come to the end of this video. If you like this video, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.